So today we're going to be talking about anomaly cancellation standard model. As usual, I start by a review of the previous lecture, and if there are questions as we go along, do ask. So a lot of what we did in this course was towards building models of quantum field theory that first exist, meaning that they are safe in the UV, they're mathematically well posed and well defined. And then we started using these models to explain various physics that could arise in the infrared. In fact, from the point of view of fundamental physics, if you have in mind some UV theory, standard model of particle physics is perhaps the most successful field theory we've constructed. It's a renormalizable interacting quantum, four-dimensional quantum field theory. It's a gauge theory, and it unifies all forces: strong nuclear, weak force, electromagnetism, and not gravity, and explains everything but gravity. So the gauge group is SU3 color times SU2 left times U1 hypercharge. And we talked about how the electroweak spontaneous symmetry breaking gives you a U1 electromagnetism and gives mass lifting the W and the Z bosons. So the gauge bosons, there are 8 gluons, right, for SU3. There are 3 gauge bosons for SU2 left. These are the things that turn into the linear combinations into W plus minus and Z. And B mu Z, Z and B mu. Z is a combination of W3 and B mu, and then the orthogonal direction, we saw that it was a photon. All right. We said that the matter content of standard model is 3 generations of fermions. We had leptons. Leptons were the fundamental fermions that did not interact through strong force. They come in 3 generations. We packaged the left-handed electron muon and tau, E1, E2, E3 in our notation with their corresponding muons, and they form the SU2 left doublets, right? We use the Majorana notation, but I said that several times. The Majorana is a matter of convention. Here are the charges. So then we have the quarks. So the quarks are, of course, interacting through the strong force. What representation do they have with respect to SU3? They're fundamental. And that fundamental is clear in the 3 here in the representation theorem. So the up and down left-handed, of course, form a doublet SU2. And we went over this several times by now. These are the hypercharges. Because these particles are Majoranas, their antiparticles are the same. Well, the antiparticles, you know how to construct a representation theory, right? The U1 hypercharge is flipped, and the generators of these guys are going to be the generators of the complex conjugate. Higgs was the only massive particle that we allowed in the theory. It's a complex scalar field that transforms as 1, 2 minus half. So 1 means that there's no strong interactions, indeed. 2 means there's SU2 doublet, and minus a half. And why did we have to put something non-zero? Why did we have to have some non-trivial representation here? Because we wanted spontaneous symmetry breaking and we wanted mass in the universe, right? And that we explained, went through. So here's like a 1-slide summary of a lot of what we went through. This is the matter content. I'm not going to repeat that. We went through that last time. But here I want to highlight all the vertices of the standard model. So of course, gluon. So this is the SU3 part. That is, hopefully you recall, it's pretty standard from the non-abelian gauge series. Then we had the Z and W bosons, right? So the Z, we called it the neutral current, and it's coupling to the fermion. It violated a particular discrete symmetry. What was it? CP. No. Z. Z violated P. CP was violated by the charge. I'll repeat that, right? So W plus, W minus. And the violation of it had to do with the fact that, so after we diagonalized the masses, the only flavor changing physics were in these two vertices, right? So, and that has to do with the so-called CKM matrix, right? Now, right, okay, so we said that here, of course, the SU2 sector has the standard gauge interactions, right? This has, how many momenta are there in this vertex? No, momenta. There's one derivative here. There's one derivative and one structure constant. This guy has no derivatives, two structure constants, right? All right, and then these are the Higgs. So a few comments that we made last time was that these are observational comments. It's a fact that there's mixing angles. Mixing angles were the way that we parameterize the CKM matrix. Experimentally, you have observed to be seen this way. They satisfy these properties. Well, they're in this particular order. It's not known. It's an open problem. It's, I guess, nobody knows why the mixing angles are small, right? So it means that fermion flavor changing physics is suppressed in standard model in nature. There's no explanation of this. Maybe your generation one day will come up with an explanation of this. We saw that the CP symmetry is preserved if the CKM matrix can be made real. And we said that is pretty darn close to real, but it's not real, right? So there's CP violation in the charge current coupling to leptons, right? To quarks, sorry, quarks. The leptons, there are no CKM matrices for the leptons. And the reason for that was no right-handed neutrinos, indeed. All right, we precisely as we just said, there are no right-handed neutrinos. The consequence of which is that the lepton W boson interactions are always proportional to G2. There are no extra parameters, right? That we call the weak universality. Then towards the end of the last lecture, I summarized again the discrete symmetries that we discussed in QFT1, and we saw that CP and CP equal to T. First we said that CPT is the symmetry of any quantum field theory in 4 dimensions, right? In fact, it's a symmetry of any quantum field theory in any even dimension. In odd dimensions, I said in QFT1 that there's another symmetry, right? It's CRT, reflection. So Higgs interactions satisfy all of them. Gluon interaction is the same. Electromagnetic the same. Neutral current interactions violate C, but preserve CP. Do you remember what was the cause of that? I pointed out what is the origin of that. It was gamma 5, right? It was the gamma 5 that was the origin of this violation. And then the charge current interactions violate CP, of course, right? Equivalently, they violate T. And that had to do with the fact that the CKM matrix could not be made real. And then we ended last time by a quick summary of, well, your generation is going to go beyond Standard model. Standard model is now 50 years old. There are open problems. The red ones that are very, very important, meaning that we absolutely need to explain them. There's dark matter that is not included in standard model particle physics. And dark matter, why do we call it matter? It's because its energy density scales with the volume, right? We said that was important to call it matter. We said it's not baryonic, and it makes up 26% of the mass energy in the density in the universe. Then we also said that there are neutrino oscillations, which is not allowed according to standard model particle physics, and it points towards neutrino masses. Now, your last homework, as I said last time and it's now posted, you have a homework problem about including right-handed neutrinos, how it would add neutrino masses for neutrinos, and what extra parameters is going to result in the standard model. And then you'll play around with it and you'll learn a little bit about how like how would you go beyond standard model and what are the problems you're going to face. So then there are three other problems that I listed, which are not killer problems, meaning that we don't absolutely have to explain them, but these are, from the point of view of theory, are odd. These are fine tunings, right? This the example of fine tuning that I always have, and I always repeat that, is like if you open a door to a random classroom and there's this pen standing on its tip. That satisfies all laws of physics. Nobody's holding it. However, it's fine-tuned, right? A tiny perturbation will mess up your configuration, right? So baryon asymmetry was one of them. Baryon asymmetry is a statement that there's a lot more matter than antimatter in the universe. This is completely consistent with everything we know about the universe. It's just, I guess, the initial conditions of cosmology that you're given. We don't know why. We said that the CP violating term, the failure of the CKM matrix to be real, is not large enough to explain this. There's a strong CP problem. What was it? The theta parameter is not zero. Theta parameter is a violation of CP in the SU3 sector. Now, what was the logic behind this? The electroweak doesn't preserve CP, right? So if it's not a symmetry of nature, why is it the symmetry of half of the theory? Why is it the symmetry of the SU3? Now, in principle, people who wrote down standard model particle physics to just that this is what the model is, right? It's a symmetry of these terms, not a symmetry of those terms. But we explained throughout QFT2, we've built this intuition by now that every time you come up with such a setup and there are some terms that violate the symmetry with small amount, that we did say the violation of CP is suppressed, it's usually an indication of spontaneous symmetry breaking. And I hinted for you guys to go and learn about how axion, the whole theory of axion, is about spontaneous symmetry breaking mechanism that will give you an explanation for why this is the case. Then I mentioned hierarchy problem, which is from the point of view of low energy observers, low energy physics, it's odd to have massive scalar. Why was that?
It grows in the UV.
Yeah, mass is always relevant, so it grows, right? Now, it's silly from a fundamental perspective to include a mass term and treat it as perturbative, right? Because if mass is going to be order one, things are going to be strong, right? Because mass always grows towards the infrared. If you have a perturbative mass at this scale, it means that the high energies, this was a teeny tiny amount. Okay. All right, so this is a quick summary of the last lecture. Are there any questions? All right, so today is the last lecture on the standard model. And what we're going to go over is we're going to talk about anomaly cancellation in standard model. This is very important. We said that in the model, we have chiral fermions that are charged under a gauge symmetry, right? This is the gauge group. But every time you write down a theory and say you have chiral fermions that are charged under some gauge transformation, you must check that there are no anomalies. Anomalies means that it's just inconsistent to include charged chiral fermions. It's just not a sensible thing to do, right? We went over this in detail and what we spent the whole lecture on this. I'll quickly review that. The analysis that we did was two-dimensional for simplicity. Today, I'm going to review it, do a four-dimensional example of fermions, and then we're going to do together a calculation of chiral anomaly for charged fermions of standard model and see how term by term they all cancel. Now, here's your first indication. When I was a grad student, I learned this. It blew my mind. And to this day, it hasn't changed. It still blows my mind. You'll see that the cancellation of anomaly in the standard model crucially depends that there are three generations and the charges have to be those exact those exact values and number of generations have to satisfy an equation. So it's not like when I was presenting Anomaly, I said, okay, there are 3 generations. Okay, that's just a fact. So you might have said, okay, what if there are 4 generations and the other fermions are just very massive? The moment you put 4th generation, even if they are very, very massive, you have the problem that your anomaly cancellations, your anomaly might not cancel. The theory is just inconsistent, right? So we're going to go over that. That will be the punchline of this lecture. But it is important that this is the holy grail of the whole course. Right? We've built so much, we've learned so much about quantum field theory, and this is the theory we've constructed. We want to make sure that it makes sense. It's not inconsistent. All right, so to go over that, the gauge transformation of Majorana fermions is this way, right? This is the gauge transformation of it. These T's and T stars are the generators of whatever gauge group you have, right? And you could explicitly check that the Lagrangian Anomaly that I wrote down is just by construction is classically the Lagrangian invariant under the gauge transformation, right? This transformation. And the question is that whether it's anomalous or not means that does this symmetry survive in the quantum world? Is it an actual symmetry? Or do quantum effects ruin it? Now, if it's just global symmetry and quantum effects ruin it, that's still okay. But for gauge invariance, it's nonsensical. We said this before, and I will repeat it again. Well, at the level of this course, it's nonsense. Once you dig a little bit deeper into mathematics of quantum field theory, you learn that there's it's a nuanced state. But it is crucial for Anomaly particle physics. It's absolutely crucial that the Carl anomaly matches. All right, so where does it come from? Consider QED coupled to massless fermions in 4 dimensions. Well, sorry. Consider QED in 4 dimensions with massless fermions, right? That's what I meant to say. So just massless electron and photon. That's this very, very simple theory. Here's the action for it. You know exactly what it looks like. There's only one vertex, right? It's a pretty trivial theory. And I'm using this as an example of reminding you of the representation theory Lorentz group and how it worked. So we used Dirac matrices to construct a representation theory. Gamma 5 was gamma 0 to gamma 3 multiplied, right? Which is this diagonal matrix like this. In 2 dimensions, we saw, and in 4 dimensions, similarly, there are 2 types of gauge transformations. There is a so-called vector transformation this way, and then the axial transformation this way, right? So you can see that because of this matrix being block diagonal like this, the fact that it's block diagonal like this is a statement about what exactly? It's, well, 1 plus this divided by 2, or plus minus, are projections to left and right chiral modes. So the 4 degrees of freedom of a massless fermion in 4 dimensions in representation theory Lorentz group, we said is reducible to a direct sum of 2D, two pairs, 2 chiral modes, right? And yeah.
Sorry, why does mass spoil that reducibility?
Why does mass spoil it? Someone say this.
I mean, even with mass, isn't Dirac fermion 1/2 0 plus 0 1/2 in Lorentz representations?
Say it again. Say it again.
So isn't, I mean, Dirac fermion is 1/2, 0 plus 0, 1/2 bar.
Oh no.
Right?
No. We're talking about this.
Yes.
What is this? This is a massless Dirac fermion. A massive Dirac fermion, not this. Not at all. Just write down. Okay, so there was a homework problem about this a while ago, or in QFT1 actually. Go back there, write down the mass term, and see explicitly what the. I think I actually have it. I had the slide here. Oops. All right. It's explicitly violating the. it violates the J axial. So it gives your right hand side to del mu J mu A.
So in representation theory, I couldn't write a massive direct experiment.
No, that makes no sense. Yeah. Why is that? Because the mass term takes you from this sector to that sector, right? I mean, remember what the philosophy was. Why do you write things in terms of irreducible representations of the Poincare group? So that they remain, a particle that propagates remains the same particle as time goes by. Now, a massive particle, if you decompose it this way, is only sensible at a particular instance in time. Right? It makes no sense. All right. Okay, so this is pretty straightforward. This is from QFT1. There were two conserved currents, the vector and the axial one, right? Those are what they are. And here are the classical conservation laws. Now, to make things a little bit simple, I remind you of the 1 plus 1D example explicitly. Here's what the Lagrangian density was, right? Here the chiral modes are the left and right movers, right? And here are the vertices and here are the projections. What were the conserved charges associated to these two independent U1s? It was the charge density, is the density of the right movers plus left movers was one, and then the density of right movers minus left movers. Now, the inclusion of mass term here spoils that. Why? Because it couples the right movers to left movers, precisely, right? So they can't possibly be conserved. Now, you have two independent conservation laws. The sum survives, right? But the difference doesn't. That's why the axial one is violated, but the vector one is preserved, right? As a certain amount of, left movers under time evolution can transform to left movers can transform to right movers, but the total amount is preserved. That's why vector is preserved. All right. In this case, I just want to remind you, we went through this calculation in detail, but I just want to remind you that a phenomenon that was very important was that is essential. It might be a little bit counterintuitive, but that in 2 dimensions, photon becomes massive in this theory, right? And the reason that usually violates gauge invariance, but here it was okay. Why? Because there was a massless mode in the spectrum, right? If you recall, when we did the vacuum polarization QFT1, and I repeated that calculation QFT2 earlier in the course, we said that massive photon completely messes up phenomenology, physics, right? The discrete matching with the what we see in the world. And the reason was that the loop corrections for so we had this. The reason was that, so here's what vacuum polarization was at one loop, right? So if this guy is massive, which is like a fermion, an massive electron running in here, it would lead to a mass term due to this would lead to a violation of gauge invariance. That's awful, right? Well, that's just nonsense, right? In 2 dimensions, actually 4 dimensions as well, if this is massless, that argument is too quick. We redid the argument and we saw that, in 2 and 4 dimensions, it's possible to have gauge invariance and have a mass for photons, right? Because the analysis was coming from poles, right? We're counting poles. When you have a massless mode, the pole structure is different. So this was the explicit expression. Like we talked about amputated diagrams. So in amputated diagram, that's this, which is this diagram, right? So in 2 dimensions, this is the expression for this diagram. And what is neat is, it's amusing that this integral doesn't need regularization or anything. We just do it. In 4 dimensions, we had to. introduce infinity, cutoffs, all that song and dance. 2-dimension, you can do it. The theory is super normalizable, right? You can just do it. This integral is trivial. If m squared is 0, this x 1 minus x and x minus 1 minus x cancel. This q squared comes out, and you get this expression. What is this? After resummation, remember, and right, this resummation that we had, after this resummation, this term is precisely what gives you, we call this pi, right? This is what gives you mass. So now, another fun thing about 2 dimensions is that this photon mass that we just calculated, e squared over pi, in one loop, is exact. It's correct. It's a full answer to non-perturbative to arbitrary orders. And then you ask me why? Because 2D QEDs, massless QEDs, very simple. You can just explicitly non-perturbatively solve it.
Right. Whenever we introduce that symmetry in the propagator corrections, we always assume the series converges without proving it.
No, it's not. We did a formal resummation, right? So we said that this guy is like, let's say pi mu nu, which is pi proportional to whatever gauge invariant construct. Let me just write it down. Right? This guy. Now, call this pi. Well, once this is pi mu nu, what this summation of this resummation. So 1 plus these corrections will end up being 1 minus this guy, actually, right? So you're absolutely right about the fact that I'm hiding a whole bunch of things under the carpet. This guy is divergent, and I'm summing a whole bunch of divergent pieces, repackaging it this way. However, so these statements they all have like this resummation has a radius of convergence, which is actually this guy, the absolute value has to be less than 1, right? But as dim reg, we talked about this magic, right? Dim reg is, this is the dirty algebra that we do in quantum field theory, and making this mathematically rigorous is incredibly difficult. It's still work in progress. It's like there are certain aspects of it that are not fully properly understood. I can only point you. I can. It's a little bit outside of my field of expertise. I don't know much about how to make this rigorous, but I can tell you that there is the so-called Schrödinger representation of propagator, which is a way of cutting off. It's a nicer way of cutting off the UV, which gives you a physical interpretation for dim reg. Right. So dim reg was the mathematics of it. All right. Any other questions? So what I reviewed so far was the 2D calculation of, well, actually, the story of what axial anomaly was in 2 dimensions from massless QED. I haven't quite reviewed it. I just started, and now I'm going to finish the story. So what do you want to calculate? You want to calculate the vertex, the vector current, right? So what are we after? We're after we want to calculate the right-hand side of this, right? That's what we want to calculate. Now, is it clear that this is the diagram I have to compute? Hopefully that's clear, right? So this is what we want to compute. And the trick that we just discussed, the reason that we went over the vacuum polarization is that, well, if you look at this diagram, you look at the amputated diagram is the same as vacuum polarization. So we recycled that calculation, right? That was the idea. So here's the calculation that we just recycled from the 2 slides ago. From this expression for J, you could just take derivatives, or in Fourier space, you could just do Q mu, and it's 0. So del mu of JV being 0 is the statement of gauge invariance. It's the statement that the propagator remains proportional to this. It's a word identity. right? Now, in D equal 2, there's this. So this is the vertex one. What is nice is that because, so how do we get the anomaly of the axial one? You have to use gamma 5, right? And there's a bunch of, the Dirac algebra tells you how to relate JV to J axial, right? So you could use the Dirac algebra to do it. In 2 dimensions, there's this nice expression, right? Which allows you to write Q mu J mu A axial in terms of the V1, right? Now you're contracting epsilon mu nu with the propagator, the transverse piece of the propagator. And here's where the anomaly comes from, right? You just contract this, you get epsilon mu nu F mu nu, right? This has a name. What is this? It's a dual field. It's a dual field strength. It's a thing that we said we said what the dual field strength has to do. What was it in 4 dimensions? What was the physics of the dual field strength for electromagnetism?
Gives you homogeneous.
Yeah. So, no, yes, but what was the symmetry?
Yeah.
E goes to B goes to minus E, right? That was the CP, or time reversal. That's actually a nicer way of saying it. All right. So here's the anomalous word identity in D equal 2, and we calculated it. So the axial anomaly is not conserved. But this was the formal calculation that we did, and I'm repeating it, but the intuition behind it hopefully was simple, right? What did we say? We said that if you introduce a background gauge field, right, in the presence of the background gauge field, some left movers turn into right movers, right? That was what the physics was. Not even dynamical, background gauge field means electric field. You can't possibly put chiral fermions in a background that has electric field and keep them chiral, right? That's the inconsistency. So what in the language of Sano model particle physics, what does it mean? It means that we wrote the action of Sano model, it's all good and nice. Now, the moment you say some of these gauge fields have background fields, like electric field, there's you have a medium with electric field or magnetic field. All of a sudden, your fermions are no longer, it's not consistent to have them as chiral, right? So that's why it's an issue of consistency of the theory. Of course, we want to be able to have background gauge fields. It's not the U1 that's the issue, actually. You'll see. But of course, it's not even the U1 of Sano model is not electromagnets, right? That's the hypercharge. All right, so to get this calculation done in more elegantly in 4 dimensions, I'm going to review the Fujikawa method and generalize it. So Fujikawa method was it's actually the nicest way of thinking about anomaly, in my opinion, my humble opinion. So here's what the gauge axial here are the vector and axial gauge transform. This is the axial transformation and the fermion and the antiparticle. So here's the action. By the way, is it clear why this violates the axial? You see it, right? It's pretty obvious. It's explicit. There's gamma 5 in there. And also do keep this in mind. This whole story is intimately tied to CP violation. CP is equivalent to time reversal. I already commented in the previous lecture that some of this story has to do with gamma 5. Why? Because this object is not a Lorentz scalar. It's a Lorentz pseudoscalar, right? That was crucial. And as I repeat the calculation, pay attention to the following thing. The trace of gamma 5 as an operator is what results in anomaly. What we're gonna do, we're gonna manipulate the path integral, and you're gonna see that the trace of gamma 5 is the object that contains or teaches you about the anomaly. All right. So this action doesn't need explanation. Here is the path integral in quantum field theory. Once you have a classical symmetry, it means that under the transformation, this guy is invariant. For this to not be a quantum symmetry, how could it fail? The measure it must be that the measure is not preserved under it. So, all right, let's just see how does the measure transform under this. So when you see a path integral over these fields, what you should be doing is that you first have to take the field and expand it in an eigenbasis, a complete basis of functions, right? That's what you would have to do. Now, if you had a free boson, what would this what choice would you pick for this eigenbasis?
Plane waves.
Correct, but why would you pick plane waves? Because these are the solutions to Klein-Gordon equation, precisely. So once you're dealing with fermions, you'll have to look at the solutions, the eigen solutions. Those are the eigenkets of the Klein-Gordon equation. You have to solve it, or the eigenfunctions of the Dirac equation. But here are the eigenfunctions of the Dirac equation, the eigenvalues of the. Here, the eigenvalues are here, and here are the eigenfunctions. Now, what you do is you expand your field in terms of the eigenfunctions, right? And here are the coefficients. You're going to path integrate over those coefficients, right? You're going to integrate over those coefficients. Now you have a continuum worth of it, hence the path integral. Right? So here's what this is. This is just linear algebra, right? You take a function and expand it in an eigenbasis, which are the solutions to the eigen. These are the eigenkets of the Dirac equation. And similarly for the dual guy. Notice that these A's are Grossman variables because the eigenfunctions of. All right. So here's a transformation. What is a transformation? A gauge, axial gauge transformation. All that it is, at infinitesimal one, is just I epsilon gamma phi. So you already see everything has to do with gamma phi. So the path integral, this is the measure. What is it? Psi is a vector. So think of this, I usually think of it this way. Think of this guy as a vector of, like psi. Think of it. This is a crude picture, right? This is for phi 1, A2 for phi 2. These are the eigenkets, right? And view this as it's an operator. It's a differential operator that acts on this. It's an operator that acts on this, but view this as a matrix, right? So how does it act on psi? This matrix, which is 1 plus I epsilon gamma phi, it acts on this and changes these guys. So it sends AM to sum over N CMN AM. This C matrix is the matrix that corresponds to that gamma 5. Right? It's just a matrix representation. It's the gamma 5 operator written in the eigenbasis of the Dirac operator. Now, we have a field redefinition. What is the Jacobian that you pick up? It's just the determinant of 1 plus C. Right? That's all that there is. It's just a pretty simple calculation. Now, determinant of 1 plus C, this is a matrix. This is exponential of trace of log of 1 plus C. These manipulations should be familiar. If they're not, ask. Okay? Now, log of 1 plus C, for a second, imagine anomaly is small. Right? There's a small parameter that controls it. For example, I can take a small gauge transformation. This log can be approximated by C. So you have exponential of trace of C. You have to calculate exponential of trace of gamma 5. That's all you have to calculate. And we did this before, but what did we do? Well, we have to calculate the trace of gamma 5. This is an infinite by infinite matrix. It's not even discrete. Right? It needs to be regulated. How do you regulate it? Well, you just put these Gaussian suppressions. You introduce a cutoff. What is this suppressing things by? This is so we're expanding your trace in the eigenbasis of D slash, ID slash, which is a Dirac operator. So this just says that suppress every term in your expansion by a Gaussian with the eigenvalues sitting in the exponent over some scale m squared, right? It's a very reasonable regulator. Yeah, I think last time I went through this calculation was very quick. That's why I'm sort of repeating it, and also it's helpful because it's this calculation. I'm doing it. Last time I did it, it was all in 2 dimensions, but up to here, I didn't need to say the word 2. And you're gonna see the calculation when it becomes 2D, 4D. Up to here, it's all general. So the next step is to just use this identity. Hopefully, you recall this from QFT1. The square of the Dirac operator is just d squared plus it has f mu nu in it. That's what's important. F mu nu is in there. Why is it there? Yeah, it's covariant precisely, right? Because you have background charges, background gauge fields, right? If there is no background gauge fields, there is nothing to be considered, right? It's a global symmetry and it's just perfectly fine. All right, so what we're gonna do is we're gonna take this. So here this step is kind of funky. Look at this exponent. I'm gonna expand it as 1 plus this guy squared over 2 plus this guy cube over 3 factorial and so on and so forth. Here's what it looks like. Good. Everybody's with me? Now I erased it. Trace of gamma 5 is 0. That's obvious, right? Identity minus identity. Good. So this term goes away. Oh, sorry. This is in 2, 4, and 6 dimensions. We're doing the calculation for 2 even dimensions. Now, the d square is pretty straightforward to see. Well, actually, because trace of gamma 5 is 0, this term doesn't contribute. This term doesn't contribute, right? All the terms that don't have f mu nu do not contribute. Next, what you would like to do is you would like to capture the piece that's linear in f mu nu. You stare at this expression. This piece is linear in f mu nu, right? And then there is a piece that's this linear piece squared divided by 2 and 4. So from this expansion, you could pull out, well, okay. You could, from this expansion, you can pull out this piece, and then the all other terms are higher order in f mu. Is this step clear? Good. All right. So this is the calculation of anomaly, the core of it. At this point, if I want to focus in 2 dimensions, in 2 dimensions, trace of gamma 5 sigma mu nu, which hopefully you recall, sigma mu nu is coming from representation theory of Poincare group for fermions in 2D, fermions in arbitrary dimensions, 2I epsilon mu nu, right? Epsilon mu nu, F mu nu, that's the dual field strength. That's the anomaly term. I'm gonna just flash this because we did this calculation last time, right? Once you do the manipulation, oh, sorry, this is the expression. This is what you get. Yeah, this is what you get. Good. Now, in 4 dimensions, trace of gamma, notice that the calculation is completely general. This. Trace of gamma 5, sigma mu nu is 0. So what happens? It means that to this order, there is no anomaly. You have to go to the next order. You have to calculate this term. I'm not going to do that, but it's a couple of lines of algebra. It's going to be proportional to this object. This and 4-dimensional Dirac algebra turns into epsilon mu nu lambda rho, right? That's contracted with the f mu nu to a second order. You obtain this. This is the anomaly in 4 dimensions. Now, you saw that the anomaly in 2 dimensions is proportional to f mu nu. In 4 dimensions, it's proportional to f mu nu squared, right? Do you have a guess what is going to be proportional to in 6 dimensions. But why? So here, the way I argued was that I said, well, I just use the Dirac algebra. This vanishes. This is non-zero in D equal 2. In D equal 4, the F mu nu term was vanishing. So I had to go to the next order. And that's a correct guess you made. But when you go for that to happen in 6 dimensions, the Dirac algebra has to work out so that the coefficient that sits in the first term, the F mu nu term is 0, the next order term is 0, and then it's not 0. Why is that happening? Does anyone have a guess? The answer is very, very simple. It's very simple to guess why it has to be proportional to F mu. It's not here. Okay, yeah. Now I guess, just think about it. Maybe I can help you. Can you write this equation? 4 dimensions with. Does this make any sense? Does this equation make any sense in 4 dimensions? And if it doesn't, why? As a physicist, every time somebody shows an equation, your first step, dimensional analysis, is dimensionally incorrect. Right? We're going to go over that. It has to be proportional to F mu squared by dimensionality. It has to be in 4 dimensions. And 2 dimensions, it had to be proportional to F mu. So we're going to go over that. So dimension counting. It's pretty straightforward. So what was J? Let me start here. We want to, so here's what the equation is, right? So this is dimension 1. You need to know the dimension of J. What is J? J is psi bar psi. What's the dimension of psi? It's D minus 1. Why? Because psi bar del psi has dimension of space-time, D. So D, remove the derivative, D minus 1 divided by 2 is psi. Psi bar is D minus 1. Here's your J. Good? So this guy has dimension D minus 1. This is plus 1. So the left-hand side has dimension D. Right? Now, what's the dimension of F mu nu? There are various ways of doing it, but the simplest way of doing it is that just look at the Dirac matrix. It has a term which is second derivative plus F mu nu E. It means that E F mu nu has the dimension of second derivative, which means dimension 2. So in F mu nu has dimension 2 in all dimensions. In all E F mu nu has dimension 2. So in 2 dimensions, the left-hand side is 2, the right-hand side better be 2. So F mu nu, if it's proportional to F mu nu, it has to be proportional to F mu nu. Why? Because the problem was coming up when we introduced background gauge field, background electric field and magnetic field. What is that? That's F mu nu, right? So in 2D, it was coming up when we introduced E. In 4D, it comes up when we introduce what? F mu nu, this combination of F mu nu. What is this combination in ENM?
E of B.
E dot B, precisely. It's E dot B. You have to have an electric field and magnetic field parallel to each other, right? And the dimension counting works out nicely. So for that reason, in 6 dimensions, it has to be F mu nu cube, right? All right, any questions about this?
What was the slide before this?
Oh yeah, I wasn't sure if I wanted to say this. Yeah, so the slide was this. So here's this expression that we found for the right-hand side of the axial anomaly in 4 dimensions. I wanted to say that this is the same term that we included as a theta term in the Lagrangian of QCD, could have included, and then we said CP violate. There is no CP violating term in standard model particle physics because the coefficient of this is tiny, right? So the point being that this is related to CP violation. That's the point. and it's topological. Oh, now that you mentioned it, I'm gonna tell you this. So I said this many times, that this is topological, meaning what? It means that it doesn't change the equations of motion. How do you check that? Well, derive the equations of motion from this. So it's an exercise for you. Very, we did this in QFT1 first 2-3 weeks, varying this with respect to the gauge field gives you the equations of motion. This is your extra term, vary with respect to it, and there are no corrections. It's topological.
Are all topological terms proportional to total derivatives in the action?
This is not a total derivative. It's a little bit more involved. No. The short answer is no. It's related. So this is a 4-dimensional action. It's related to Chern-Simons, which is 3-dimensional. It's D of anyway. It's a long story. Yeah. Let me not get into that.
When you check explicitly that it's the Hodge-star operator.
Yeah, that's precisely what it is. Yeah. So this is F. Sorry, no. That's the wedge operator.
They are one on the left.
It's F wedge F.
Yeah, no, but the one on the left.
Oh, what you're saying? What? Do you guys know what the left is? This is what the left. Right. Okay. Why is this topological and this is not topological? Well, okay, I haven't taught you differential geometry, but in the definition of star, there's a metric. There is no metric here, right? I didn't use the metric. I just used the volume form that doesn't need a metric. That's why. All right. Now, what did we do? We derived the 4D axial anomaly for massless QED using the Fujikawa method, the path integrals. Now, I want to point, so in 2D, we said that this was the diagram that was responsible for it, right? And we looked at vacuum polarization. In 4 dimensions, the term we have, so this was proportional to EF mu nu. In 4 dimensions, the term that we found is E squared F mu nu squared. It suggests that we should find the Feynman diagram like this. This is the so-called triangle diagram of Jakiv Adler Bell ABJ anomaly. So you have to sum these two diagrams. Usually, this is how we draw it. So if you calculate this diagram, the amputated part of it will contain the anomaly. All right. So now, what in the remaining time, what am I doing? I'm gonna calculate for you, give you a quick and dirty way of computing the anomaly term for some chiral fermion in 4 dimensions based on the matter, the gauge theory that I'm given. And then we're gonna apply that to Sanormal and see anomalies cancel. So take math. So there's something tricky going on that probably you'll have to go home and check for yourself. I'm gonna use a trick. Take a massless QED, right? There are two chiral modes, left-handed and right-handed. I'm gonna think of it as two left-handed modes. I can always do that, right? So I want to think of it as two left-handed wild fermions, and I take this right-handed guy, apply transformation to it, which was, remember, we had this epsilon minus epsilon thing, and make it, so I want to define this guy and think of it as two left-handed fermions. Now, what are the vector and axial charges? The vector charge is 1 minus 1. The axial charge is 1, 1. Do you see what I'm trying to do? Why did I think of this as two left-handed? When we had left-handed and right-handed, Q of V was the density of the left-hand charge of the left-handed plus the charge of the right-handed. These guys were adding up. Axial was canceling. Because I want to see the axial terms not vanish, I make it such that it's obvious they should add up. I just don't want to mess up my minus signs, right? So what is the trick to do that? Think of your left-handed and right-handed as two left-handed, but flip the charge of this guy. Good? So that's the trick. It's a very helpful trick. This is how we're going to think about all affirmations. Good? So this is a very simple theory. You have three of these vertices. You should think about A, axial, 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 vector, 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 axial, axial, vector, vector, axial. Good? All right. You just multiply the charges. Right? That's what it is. Because it was proportional to the charge. That's all that matters. So this is going to be QA cube of E plus QA cube of E bar. That's 2. VVV, this guy vanishes. VAA vanishes. VVA is non-zero. Good? So the violation of it appears in purely axial or mixed and axial and vector. Pure vector doesn't have a violation. Let's stir this for a second so that it sinks in. Good. Now, that's a simple abelian case. What we're dealing with non-abelian gauge theory. I'm not going to redo the calculation. The right-hand side of the non-abelian gauge theory axial anomaly, first of all, the current now carries a label, which is the generator of the group. The right-hand side is going to be, so now you're, in 4 dimensions, you have 2 Fs. Each of them carries one of the elements of the group. Here you have 1. There is something within this index structure of 3 labels of the representation, A, B, C, that sits here. Once you do the calculation in 4 dimensions, here's what it is in terms of the matrices. Right? It's just something that for adjoint representation you can calculate. This is, well, this is totally symmetric in ABC. Well, that's another thing that you need to know. All right. So what we're going to do is we're going to take this equation and compute the axial and vector anomaly for all the particles in the Stano model. Good. Okay. So first take pure SU2. Imagine this is a warm-up example to see how it works in pure SU2. So in pure SU2, you have this ABC, right? This is my vertex thing. Each of these guys ABC, right? F, B, F, A, B, F mu nu A, F alpha, right? You know. Good. So the generators of the SU2 are just Pauli matrices. Their anti-commutator is diagonal, right? So this thing with index structure of ABC is half of trace of these guys to ABC. This is 0. Why? Well, this is just identity, and all the Pauli matrices are traceless. So A of 2, 2, 2 is 0. There is no anomaly associated with massless fermions in 4 dimensions when your gauge group is SU2. Good. Now consider SU2 times U1. Now the 2, 2, 2 vanishes still, but now you could have 2, 2, the hypercharged one. This is mixed anomaly, right? Now, here instead of sigma A sits the charge of the hypercharge, for instance, right? So that's no longer, so this is just a charge. It's one dimensional, it's just a charge. So it's no longer zero. Good? All right. So this immediately applied to standard model. What does it tell you? So here's your vertex. Put SU2 here, SU2 here, and U1 hypercharge here, right? Q, TBTC. Take leptons, the left-handed. So these are the leptons left-handed, right? What does it become? It has to be, so look at this. So this is the hypercharge. Hypercharge is minus a half. That's minus a half. This is half. And then there's 2, right? Because they have a trace of this identity. This is 2 by 2. That's minus a half. What did we learn? We learned that if you include only this SU2 doublet, right? And your gauge group is SU2 left times U1 hypercharge, your theory is nonsense. It has an anomaly. Good? So how does the story change in standard model? There's also QCD. So let's calculate it for QCD. For quark doublets, the left-handed modes, this is how they transform. 3 to 1 over 6. So let's repeat this calculation. 1 over 6 is the hypercharge. This half is half. So half 1 over 6, right? Oh yeah, this is the SU2 doublet. Because it's left-handed, right? 2. And then there's a color index, 3. You have to multiply by 3. This is a half. All right? Anomaly does not vanish. But if you add them up, the total anomaly vanishes. So SU2, SU3 color times SU2 left times U1 hypercharge, this anomaly vanishes. For which one did we calculate? We calculated it's for in the notation. I'm going to invent a notation to simplify my life. So this is the thing. 1, 2, 2. Meaning what? This was Q. This was TATB, right? SU2 left, SU2 left, U1. This is the one that I calculated. I have to calculate 1, 3, 3. That I can recycle the calculation of this 1, 2, 2. I have to calculate 3, 3, 3, 3, 3, 2, 1, 1, 1, 2, 2, 2, all of these. So we saw that actually 2, 2, 2 vanishes. A similar, you can repeat the argument for 3, 3, 3, that also vanishes. Now here's the funkiest one. This is my absolute favorite one. So this is 1, 3, 3. Okay, so it's hypercharge, SU3, SU3. So this is the Q, and these are the SU3s. Good. All right. So let's first calculate what this anti-commutator is for QCD. For SU3, it's 4 over 3 delta AB plus 2 structure constant T gamma. But T gammas are traceless. This term drops out. This is just a number. So you're just dealing with this term. So basically what happened was that previously you had half delta AB. Now it became 4 over 3. You have 4 times, right? 4 times. So this trace is, this is alpha that runs over 3 in the C. So this is 3. The 3 cancels this, 4 comes out. 4 over sum of the y's over quarks. Okay, so let's calculate that. You have 3 generations. You have 2 modes. Each of them have 1 over 6. You have the left-handed guy of up, which is minus 2 over third. Left-handed guy of down, which is 1 over 3. You add them up, is 0. So anomaly free. It's all good. But if you mess up with these numbers, it's not going to work. In your homework, you'll show that these guys also vanish. Let me just check this. So the anomaly cancellation standard model uses non-trivial relations between the number of species, quantum numbers of quarks and leptons. And it's essential that they cancel. It's not unique. It's not like only these numbers work, but you still have a bunch of consistency relations. Recall that the issue was that you wanted them to be massless and chiral. Right? That was the issue. And you wanted all mass to come out of spontaneous symmetry working. All right. Any questions?
So I've read some confusing stuff about how instantons are the cause of the anomaly. Like in flat space-time, we don't have instantons, so we still have selection rules.
It's above my pay grade. I don't know. There are people who, I mean, I'm going to say something very trivial. Anomaly is a non-perturbative thing, and instantons also capture a non-perturbative thing. So one thing that perhaps that there's a reason I mentioned Fujikawa method. The Fujikawa method does not rely on perturbation theory at all. There's no perturbation theory at all, right? Whatever the action is, I don't care how you came up with your action. Somebody tells me it's classically invariant under this transformation, forget about that. All the perturbative parameters are in the action, right? Fujikawa method makes the fact that very obvious that this is a non-perturbative thing. In Feynman diagrams, we calculate these using these perturbation, in perturbation theory, you can see it using Feynman diagrams as well, but these are robust things, right? So they're highly non-perturbative anomalies. So there is actually one of the nice things about anomaly is that it gives you an idea, a rule to think about non-perturbative normalization group flow. There are anomaly matching conditions between UV and IR, because the theory, no matter how it runs, all the running is all in the action, right? The symmetry is protecting the action. All the other stuff is in the measure. Anyway, any other questions? Yeah, but I do not know what that statement is. Yeah.
So we do you not get additional anomalies at higher terms?
No, you do not. Does anyone have an answer why? Dimensional counting, but how does dimension counting show in that calculation? What was the coefficient? How did I have a term? So in that expansion, there were terms that had f mu nu squared. There were terms that had f mu nu. There were terms that had f mu nu squared. There were terms that had f mu nu cubed. How could I add them? I should have another dimension. What was that extra dimension?
1 over m squared.
1 over m squared. What was I doing? I was taking m squared to infinity. So there was a funny situation that, so if you just naively take m squared to infinity, some of them might diverge. Actually, the first term will diverge. But then the coefficient of that divergent term was 0 because gamma 5 was traceless. That goes away. All the other terms remain. Yeah, so the rest are regulator dependent. So they're not universal physics. Any other questions?
Do you know about how this relates to pion decay? I thought that was the motivating thing behind this.
Sorry, pion decay. Say a bit more.
That the pion decay is anomalous, and that's what led to the calculation of the APJ anomaly. That's what motivated.
Oh, I don't know much about it, but yeah, that sounds that sounds familiar. I do not know much about it. Coleman, look up Coleman's symmetry book. There's discussion of this.
I'm going to look at the QCD. I mean, we looked at QCD, but this thing that gluons carry two colors for some reason.
Ones carry two colors.
Yeah, it's like there's this D-hoofed doe-like formalism for because of how the color charges of SU2 behave, of SU3 behave.
Sorry. Yeah, I'm not sure. I don't know.
Is this concept that don't gluons carry two color charges?
Sorry, what do you mean?
That's because you're using, right, it's SU3, so you need 8 generators, and then you have color. So what are your generators of that group? You need 8 things, and you can do that with color chart, right? So you get your different combinations of color.
Oh,
That's what this is.
so there are superposition of colors.
Yeah, that's a way you can think of that. Yeah, exactly. So you use color to represent that.
Thank you.
Yeah, I don't know. Any other comments?
I just, so like, I know supersymmetry, you do some things, but there you actually introduce more matter, right? Is it trivial for also the anomaly canceling, like one thing I would think from this argument you would say is that, well, like, this is the content of your field, right? Because you
Yeah.
cancel anomalies nicely, right?
So supersymmetry is actually even, well, it's a lot nicer than this, because what happens is that all your particles come with their super partners, right? So there's somewhat of a duplicating, and they sit in some multiplets of supersymmetry multiplets. So your question could be answered maybe this way, that a minimal version of Standard model, which is supersymmetric, is safe. But if you come up with fancier versions where you add more matter and stuff, then you might worry about how to make sense of that. You have to check anomaly cancellation. But no matter with or without supersymmetry, the moment you change the matter content. Yeah. So actually, the anomaly cancellation could be used as a guide for what matter contents are good. You just use it to write down matter contents. Yeah. Any other questions? All right. So, in summary, this is sort of, it brings a long semester to an end almost. This was sort of the epilogue. We saw that we worked so hard to build this standard model of particle physics, which has been enormously successful, but it captures all the tools and tricks that we used. It's a 4-dimensional quantum field theory that exists, meaning that it's in the UV, it's asymptotically free, beta functions are well behaved. It's a gauge theory. That's pretty much all that we knew how to deal with. All that we used to construct sensible theories, right? And 4D. In lower dimensions, we could do better. Its gauge theory is massless, so it goes through spontaneous symmetry breaking, right? It has chiral fermions, right? It has all these nice things. Phenomenologically, it's been enormously successful, but we also comment on the fact that there is physics beyond standard model. So standard model is not the end of it. However, the fact that standard model is renormalizable, we said many times during the course, points to the fact that it is perfectly consistent to have no new matter for a while as you increase the energies. It doesn't, like that. It's possible that there is matter, there are new particles nearby, we just haven't seen them for some other reason. They're protected, they're not leading to corrections or something, right? But the point is, when the theory is not renormalizable, it means that you must have particles soon, just a little bit above. All right. We saw that so this was a sort of like a high energy perspective, but we saw that quantum field theory helps us understand low energy phases of matter and condensed matter as well. So this whole business was about, we emphasize locality and symmetry over and over again. These are the two tools that we have in our disposal, right? And just go back to Landau's paradigm again. You are a low energy observer, you start writing down, you identify your symmetries. You're irreducible, you look at the irreducible representations, your symmetry groups that defines your particles and fields types. Write down Lorentz invariant actions for those, expanding in powers of the field and derivatives. those are your low energy quantum field theories, right? That's just Landau's framework. That's how you should be approaching it. And yeah, this is the end of the story for now. The next two lectures, I guess we voted on entanglement and maybe a little bit of OP, hopefully. So we'll be talking about some non-perturbative effects. But are there any questions? Yeah.
I'm a bit confused by the fact that we always say that the standard model is just a effective field theory, which means we don't require it to have a good behavior in the true UV region, right? I mean, an effective field theory only require this kind of theory.
Yeah.
To
So-
behave well at some under some certain energy level.
Yes, yes.
Yeah, but you just mentioned that.
So there's history behind this. Ask your question again if I don't answer it. History of this is the following. For a while, people thought that, at least in particle physics, the attitude was that a quantum field theory that's not renormalizable or quantum field theory that's not UV safe should be thrown out, should be thrown in garbage, right? And this was the time that effective field theory was not used widely in particle physics as much. There were some EFTs that were non-normalizable when people used. But the narrative was that, oh, if the theory is not safe in the UV, it's not good. But over time, people started realizing that even though the theory might be non-normalizable or something, effective field theory is extremely valuable. This was perhaps like known to part of the community all along, but there was the obsession that high energy theorists had with a completely consistent theory writing this down. That's why, like when Anomaly was proven to be, well, I don't know what is the description of the Nobel Prizes, but like it was considered that like when people figured out that it's renormalizable, it's anomaly free, all of that, there was a Nobel Prize given for this. Now you could say that it was for the success, phenomenological success of the theory, but it played a crucial role for people taking the theory seriously. Nowadays, I think EFTs are just fine. EFTs are just fine, but if they're if they're renormalizable, you have more control.
Yeah,
perturbative
I
control.
mean, the standard model is normalizable, right?
Yeah.
Yes, so why we still call it effective field theory?
Oh, because because we do know there are new particles, right? We do know that there's beyond standard model physics. Yeah. It can't be the full story.
The question is, what is that scale? Right?
Yeah.
You can argue maybe it's gravity.
Yes.
But is there something really nuanced?
Yeah. Actually, I think
Oh,
that
I got it.
reasonable.
So is that kind of like we know there is some higher energy scale?
Yeah, exactly. Yeah, so actually, that was the reason I mentioned beyond standard model. The first two problems that I mentioned, right, dark matter and neutrino oscillations, tell you that there must be physics beyond standard model. The other ones you might sit down and argue forever, right? But the first two, it must be that it can't be the full story, like can't be the whole story. And then there's gravity. Of course, gravity tells you that there's. So just have things in mind, right? So this is energy scales. 10 to 19 GeV. This is Planck and Planck. There's 10 to 16 G. These are all approximate. This is called gut scale. General, grand, not general. Grand unified theory, right? Then there is the, what is the number? 14 TV.
For electroweak, is
No. What is
I
the
see, 13.6.
13.6 TV? This is how far we see, right? Then there is the 250, say GeV or something, right? That's the electroweak, 200, 100 something GeV, right? This is the electroweak, spontaneous retrography. Then we had the, what was the other scale? 500 MeV, right? QCD, this is the confinement. And then there's low energy physics, there's a lot going on here, right? So, Yeah, this gap is enormous. It's an enormous gap. Now, neutrino mass and neutrino oscillation, I'm not an expert at this, but there's a so-called seesaw mechanism. The most natural models of neutrino oscillation point at some new modifications at this scale. And there are other reasons to believe that this is an important scale. But at least to my understanding, my knowledge, in between, we don't really know what's going on.
Humanity won't get to those scales anytime. Or how do you see it?
You know, okay, let me pause this.